think of the generator as being a kind of a reverse convolutional neural network. With CNNs, or convolutional neural networks, the goal is to transform a 2- or 3-dimensional matrix of pixel values into a single probability. A generator, however, seeks to take d-dimensional noise vector and upsample it to become, for example, 28 times 28 image here in this example. This upsampling is done through a convolutional transpose, which is also called deconvolution layer. ReLUs and batch norm are then used to stabilize the outputs of each layer. So this part of the code shows the architecture of the generator that we have written here. The structure of the generator is very similar to the structure of the discriminator, except that we're calling the convolution transpose method instead of the convolution one. The convolution transpose plus ReLU plus batch norm pipeline is repeated 4 times here in this part of the code, so that the output volume grows larger and larger until we would get a 28 times 28 image. The number of the filters of the first layer of the generator is set to 64 and the color dimension is set to 1 since the images are grayscale. So this is the first deconvolution layer that we have. The number of the inputs is equal to 64. The color dimension is equal to 1. And the output size would be equal to 28 because we want a 28 times 28 image at the end. Actually, we want the generator to generate fake images which look like real images of this size, 28 times 28. We want to start with a noise vector and get matrices after each deconvolution layer, and we would like to have gradual increase in the size of the matrices in order to get the 28 times 28 matrix at the end, or image at the end. These determine the gradual increase in the size of the output image. The output size is 28. Since we want to slowly upscale the image, we generate different upsampling factors, which, as I said, are called S2, S4, S8, and S16, and apply the ReLU function on the vectorized input. Each layer would be upscaling by a specific factor like S2, S4, S8, and S16. The first layer gets a 2 times 2 noise image and upsamples that to a 3 times 3 image. It uses a 5 times 5 kernel initialized with normal values, and the bias term is also randomly generated. Then the transpose convolution is applied with strides of size 2 times 2. To increase the stability of a neural network, batch normalization normalizes the output of a previous activation layer by subtracting the batch mean and dividing by the batch standard deviation. So that is the reason why we apply the batch norm to the previous result. After the ReLU activation function is applied, and the output would be of the size batch size times 3 times 246, in which 256 is 4 times the input size, which was equal to 64. You can see this part of the code which shows the structure of the first layer that I was talking about. The kernel has the size 5 times 5, and you can see that we have applied the transpose of the convolution here and added the biases and used the batch norm here. After that, we have applied the ReLU activation function. The same method is used for the second layer, which has the output size of batch size times 6 times 6 times twice the size of the input, which would be 128. The output of the third layer is equal to batch size times 12 times 12 times 64. The fourth layer also follows the same structure, but the output would be computed as the tangent hyperbolic of the transpose conv 2D result, which would be in the range between -1 and +1. This shows the structure of the fourth deconvolution layer. The third one was just like the other two ones above, so we skip the explanation of that one. So the output of the fourth layer would be between -1 and +1. The output size of this last layer would be batch size times 28 times 28 times 1, which is equal to the size of the image that we have in the training set, because remember we were looking for images of size 28 times 28. Now that we have defined the discriminator and the generator functions, let's train the generator with noises. As I said, the generator receives the noise in the beginning and tries to get generate the fake images that look like the training images that we have in the dataset. Since we changed our batch size from 1 to 16, we need to reset our TensorFlow graph. In order to start the evaluation of the tensors, we call a session and determine the shape of the inputs to the generator and discriminator by using the placeholder that you can see here in these lines. As you can see here, we have a placeholder for X and a placeholder for Z. So this X needs a placeholder for input images to the discriminator, and Z needs a placeholder for input noise vectors to the generator. The loss function is a little bit more complex than that of the traditional convolutional neural network classifiers, because in the traditional CNN classifiers, a simple MSE or mean square error or the hinge loss would do the trick. But here it's a little bit more complex. If you think back to the introduction, a GAN can be thought of as zero-sum min-max gain. The generator is constantly improving to produce more and more realistic images, while the discriminator is trying to get better and better at distinguishing between real and generated images. This means that we need to formulate loss functions that affect both networks, the generator and the discriminator. So we need two loss functions. dx will hold discriminator prediction probabilities for the real MNIST images. gz holds the generated images, and dg will hold discriminator prediction probabilities for generated images. You can see them here. We want the generator network to create images that will fool the discriminator. The generator wants the discriminator to output a 1 or positive sample. Therefore, we want to compute the loss between the DG and label of 1. This can be done through the tf.nn.sigmoid cross entropy with logits function. This means that the cross entropy loss will be taken between the two arguments. The with logits component means that the function will operate on unscaled values. Basically, this means that instead of using a softmax function to squish the output activations to probability values from 0 to 1, we simply return the unscaled value of the matrix multiplication. This is where we have used this tf.nn.sigmoid cross entropy with logits. The reduce mean function just takes the mean value of all of the components in the matrix returned by the cross entropy function. This is just a way of reducing the loss to a single scalar value instead of a vector or a matrix. And the loss would be the summation of the two losses that we have. Now let's think about the discriminator's point of view. Its goal is to just get the correct labels. Output 1 for each MNIST digit and 0 for the generated ones. We'd like to compute the loss between dx and the correct label of 1, as well as the loss between dg and the correct label of 0.